I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. Thank you for the weekend just completed. Just pray to be with us today. Help us to, again, Lord, glorify you what we do, and just help us understand a little bit more about your creation, Lord, together. In the name I pray, Lord Jesus. Amen. All right, so this is lecture 22, I suppose. This begins the third part of our course, which is on rings and fields. So today, I'll be covering a good part of chapter 12 and 13. Where'd it go? Of Galilean. So let us begin with the definition of a ring. A ring is a set, a non-empty set, that has two binary operations. All right? So let's write it out here. In particular, so here's the definition. We usually use R for the ring, non-empty set. With addition, and the addition, we think of the pair mapping to A plus B, and multiplication, we think of the pair A comma B mapping to AB. We'll use juxtaposition for the multiplication. These are assumed to be binary operations. And these operations, addition, multiplication, which satisfy the following. One, we have to have that A plus B is equal to B plus A. Two, we have to have that A plus B plus C is equal to A plus B plus C. Three, there exists 0 in the ring for which A plus 0 is equal to A. For all A in the ring. Let's see here. In the previous two, to be clear, this is what? For all A and B in the ring. This is for what? For all A, B, and C in the ring. I keep changing my R to double R. That's not what I want. For each A in the ring, there exists minus A in the ring with A plus parentheses minus A equal to 0. All right. 5. 5, we have that A times B times C is equal to A times B times C. But here I mean the product of B and C first, then multiplied by A, or the product of A and B first, then multiplied by C like this. And that's also for all A, B, C in the ring. 6, we also have that A times B plus C is equal to AB plus AC. And furthermore, B plus C times A is equal to BA plus CA, and that's for all A, B, and C in the ring. Any questions? Yeah.
So are we always going to call this additive identity 0?
Yeah, the additive identity will be called 0. So when we, Now, let's see here. Yeah?
So there doesn't have to be a multiplicative identity?
Nope, there does not. Yeah, you see nothing about, we'll get to that soon, but that's extra. Not part of the basic terms and conditions here. Now, I would point out that 1 through 4, right? These 4 together make R paired with addition an abelian group, right? If you look at it. So the first 4 things basically say a ring is an abelian group. Also, the other thing I'm assuming, of course, is that addition is a binary operation. So the fact that addition is a binary operation, paired with the first 4 axioms here, that makes every ring we're thinking about, first and foremost, an abelian group. Now, it's not a multiplicative group. The existence of 0 is going to spoil any hope that there is for having a multiplicative inverse of everything. All right. But anyway, that's the starting point. Before I even get to examples, though, I need to get more terminology. So definition. Sorry, a little bit more. So 5 is what? This is associativity of the multiplication, right? And the last one is known as the what? Right, these are the distributive. This is right distributive. And this is left distributive. I think. Yeah. So, of course, the right and left distributive laws, you know, these have been hammered into you in high school algebra, right? This is how we factor, this is how we multiply, right? This is how we should multiply. We should not FOIL. We should distribute, right? It's safer, it generalizes. All right, anyway, so if AB is equal to BA for all A and B in a ring, then R is a commutative ring. So if we talk about a commutative ring, it refers to the multiplication. The addition is automatically commutative. That's part of the definition of ring, right? Otherwise, if that's not the case, if there's even one pair of things which don't commute, it's a what? It's a non-commutative ring, all right? 2, if there exists 1 in the ring such that x times r, 1 times r is equal to r times 1 for all r in the ring, then R is said to have unity 1. Moreover, R is said to be unital. In other words, a unital ring is a ring with unity. All right? So we need more terminology. So continuing in this onslaught of terminology, you got to hang with me here for a little bit. Eventually we'll get to examples. Divisibility theory is pretty much the same. All right, so like if we have A and B in the ring, and there exists K in the ring, such that, let's see here, let's try to stick my notes. A is equal to KB, then we can say like 3 different things about this, right? This says what? Right, B divides A. It also says that B is a factor of A. And there's another thing we can say here, turn the tables a little bit. We can say that A is a multiple of B, right? Those 3 statements are equivalent. Yep.
To go back for a second.
Sure.
For the unity, that's not necessarily, like, 1R doesn't have to equal R for that to be true.
Oh. There you go. In fact, it does. Yes. Now, 1 doesn't have to be the number 1, though. That 1 is a symbolic thing, right? If you wanted to be obnoxious, you might say that 1, you might replace that with like a 1 sub r for the sake of your thinking. Because you might be working with a system, a set which has the number 1 in it, and yet 1 is not functioning as the unity. In such a context, it would be useful to use this notation 1 sub r for the 1 of the ring. Yeah.
Could you write E like in past communication?
Could you write E? Yeah, I suppose that would also be good. Sure. But I would caution against going too far with that because, again, a ring will never be a multiplicative group because of 0. At least not interesting rings. Maybe, I'm trying to think, maybe the ring which just has 0 in it and 0 is equal to 1. That's probably also a multiplicative group in a stupid sense. So setting aside that very annoying and stupid example. Yeah. Okay, so, sorry, stop talking about stupid things. We've got enough election coverage as it is. Let's see here. If R is a unital ring, all right, and A is an element of R, such that there exists B in R with AB equal to 1, right? Then A is a unit. So a unit in a ring is an element which has a multiplicative inverse. This only makes sense if we're talking about a unital ring. You can't have a unit in a non-unital ring. It doesn't even make sense because you have to have a unit which you can multiply to get, a unity which you can multiply to get to. Anyway, A is a unit, and we write B is equal to A inverse, okay? 3, suppose A and B are in the ring, and A and B are non-zero. If AB is equal to 0, then we say A and B are 0 divisors. All right. Theorem. 1 in R is unique if it exists, and A inverse is unique if it exists in a ring. The same arguments I gave you on day 1 hold true here. All right? If there is a multiplicative identity, it has to be unique. If there's an inverse for an element, it has to be unique. We can reiterate the same arguments we made day 1 in here to prove. So that means like my notation A inverse is not a bad notation, right? A inverse isn't a set of things. It's a specific thing if it exists. Finally, Zx on a ring as follows. So we also use the following notation like we do in additive groups. What's n times A? It's either equal to A plus plus A, n full times, right? Or minus n times A is what? Minus A, sorry, to be more specific, minus A plus minus minus A. Again, n full times. So we can multiply, so-called multiply, an integer times the ring element by either repeatedly adding or repeatedly subtracting. Okay. I'm using a dot because it's not the multiplication of the ring. It's just a slick notation for repeated addition or repeated subtraction in the ring, right? Okay, fine. Excuse me. So let's look at some examples, finally. So what are examples of rings? Where do I keep putting my mouse? Here, there. I've hidden my markers in plain sight. I'm sorry? If yeah, that automatically follows, but it suffices to show that AB is equal to 1. We can prove in this context that if you have AB equal to 1, you get BA equals to 1. So we'll keep it. We'll keep the definition lean and just put this that way. When you'll thank me for that, because now when you're asked to prove something's a unit, you have half as much work. So if you'll forgive me for not also writing here a BA is equal to 1, even though that pedagogically that's true, but we could prove that that automatically follows. And in fact, that goes back to just a general, and it's kind of funny because I got this, I think, out of Galian, says this, and his definition of group, right, he assumes left and right inverses. But if you look at like Rotman, for example, he'll define the group just in terms of left inverses, and then he proves from associativity that the right inverses automatically follow. So I don't know. Okay, moving on here. Example. Actually, I'm going to divert from my notes a little bit here and just give you another definition so we can make the examples count. So here's our next definition. We say R is an integral domain. All right, what's an integral domain? If R is a commutative ring with identity, and R has no zero divisors. So an integral domain is a commutative ring with identity with no zero divisors. And let me just finish it here. We say R is a field, all right, if R is a commutative ring with identity. Where every non-zero element is a unit. All right, I got one more definition to give you, and I'm actually do examples. Finally, U of R, all right, so let R be a ring, okay? If R is a ring, sorry, let me back up here for a second. Let R be a ring with unity, or in other words, a unital ring. Then we can define U of R to be equal to R and R such that R is a unit. So this last thing I've defined is the so-called group of units in a ring. All right. I think we have all the terms we need now to play with some examples. So let's start out with the most basic and central example. R equal to the integers with respect to the usual addition and multiplication. Multiply, listen to me. Multiplication. Now, is that a ring? Is addition of integers associative? Commutative? Yeah, right. I mean, we know that the integers form an additive group. We studied this before. We also know that multiplication, I mean, this is really the integers, honestly, folks. The integers are the quintessential ring. This whole definition is modeled in part after it looking like integers, right? So yeah, integers form a ring. But now we can look at some more nuanced questions. Is it an integral domain? Yeah, I think it is, right? Because if you have two integers, a, b equals to 0, right? What is this? This implies what? Exactly, a equals 0 or b equals 0, right? So therefore, z has no integral, has no zero divisors, right? Also, ab is equal to ba, and 1 times a is equal to a times 1 is just equal to a, right? I mean, it's a commutative ring with identity. And this time 1 happens to be 1. So, yeah. In summary, Z is an integral domain. Is Z a field? Z is not a field, right? Why? Okay, so you're looking at it in the positive sense. The group of units of the integers is just what you said. It's 1 and minus 1. Those are the only numbers which you can multiply and get back 1 from a product, right? If you look at the solution set to the equation AB equals to 1, that implies that either A is equal to B is equal to 1, or A is equal to B is equal to minus 1. Those are your solutions in the integers, right? So the group of units of the integers are just plus or minus 1. More specifically, though, if you look at 2, right? If you look at the equation 2 times x equals to 1, that implies what? X is equal to 1/2. We know how to do math and rational numbers, right? So admittedly, we've left the universe of the integers, but it's okay. We know rational numbers, but this is this is an element of Q, right? 1/2 is not an element of Z, right? So in other words, 2, not a unit, and 2, of course, is not equal to 0. So there you go. There's a non-zero element which doesn't have a unit. The integers are not a field, right? Example 2. What if we look at R equal to Zn, Z mod n, right? Then what? Stink. Eventually I'll not cough. So it's definitely a ring, right? Addition is associative, commutative, right? For modular arithmetic. Multiplication is closed, right? Product of two integers mod n is again integer mod n. Is it, so let's see here. Definitely a ring with respect to the usual modular multiplication and addition. Is it an integral domain? Is it a field? Well, we do know the group of units, right? We already have a notation for this, don't we? We just called this UN, right? Some of you understand this group pretty well. Some of you. Some not so much. I'm sorry, is it too soon? Let's see here. Where are we? So the group of units is just that, right? And so, let's see, for example, if we look at Z5, right, then you guys know U5 is 1, 2, 3, 4, right? In fact, yes, here, this is all of Z5 except for what? In fact, Z5 is a field. It's an example of what's called a finite field. All right. In contrast, if you look at Z6, right, what's the group of units then? Well, U6 is what? It's 1, 2 is out, 3 is out, 4 is out, 5. That's definitely not all non-zero things in Z6, right? More to the point, because this 6 is 2 times 3, we have 2 times 3 is equal to 0, yet 2 is not equal to 0 and 3 is not equal to 0. Therefore, 2 and 3 are 0 divisors. So therefore, Z6 is not an integral domain. Sorry, I'm getting tired of writing integral. So a lot of people just start calling integral domains domains. I will try not to do that, at least right away. Questions? So in fact, you can kind of generalize this. If P is prime, right, we know the group of units is everything except for 0 in Zn. On the other hand, if n is composite, if it's the product of two non-zero, if n is the product of two non-zero, non-unit integers, right, like 2 times 3, then you know that the product of those two integers is 0, even though those two integers are not 0 inside Zn, which goes to show you that Zn for n not prime is in fact not an integral domain, right? It is a commutative ring with unity, though, right? So there's that. Oh, another definition I should throw at you. And I got to look this one up to make sure I say it right. It's called the characteristic in a ring. So this is from chapter 13. The characteristic of a ring is the least positive integer n such that if nx is equal to 0 for all x in the ring, and n is smallest, n in n, such that this happens, then we say the characteristic of the ring is equal to n. If no such n exists, then what do you think the characteristic of the ring should be called? Infinity, right? Just a little bit off, actually 0. I know, right? But there it is. That's the standard terminology. All right. If you have a ring with unity, it suffices to see how many times you have to add 1 to itself before you get back to 0. That's a little theorem, right? Like theorem. If 1 is an element of R and n times 1, which of course is 1 plus 1 plus da-da-da plus 1, n-fold times, is equal to 0. And that's the smallest such n that happens. Smallest n for which that happens, then that implies that the characteristic of the ring with unity is n. So it turns out, and that's theorem, it's pretty easy to prove. Excuse me, the proof is on page 244 of the text. So like here, Z5 is what? Characteristic what? Characteristic of Z5. In fact, the characteristic of Zn is what? Is n, yeah. I personally like to live in the world of characteristic 0 because it's very unnerving to me that you can add 1 enough times to get back to 0. I find that's annoying. I don't know, but you can disagree. All right. All right, so there's that example. I guess we should do another example. You guys by now have this definition memorized, which is good. I mean, these things are very natural, right? You probably don't have to memorize these. The real trouble here is to not overstate the definition, right? Because there's lots of things that are automatically true from that aren't the definition, right? For example, properties of any ring. Oh, I'm sorry. I'm supposed to stick with my examples. Example 3. If you look at z of x, so what this would be is like a naught plus a1x, an x to the n, such that the a sub j are in z. All right, so all I've written there is just, a formal I mean, can you put this in the words? These are polynomials with z coefficients. So in other words, polynomials with integer coefficients. You had a homework problem on these already, right? But anyway, think about this for a second. I'm not going to write a bunch. I'm just going to use words. Is the sum of two such polynomials, again, a polynomial with integer coefficients? Think about it. Yeah. How about the product of two such polynomials, where you just multiply like usual, right? Yeah. So this forms a ring with respect to the usual addition and multiplication of polynomials. Example 4. By the way, is it an integral domain? In fact, it does form an integral domain, because if you think about f of x times g of x equal to 1, 1, listen to me, 0, right? I mean, it's a commutative ring, right? If you take two polynomials, it doesn't matter. They're commutative, right? Polynomial multiplication is commutative. There's a 1 in there. It's just a very boring polynomial rather, just 1, right? 1 times f of x is equal to f of x for any polynomial f of x. And also, if you have the product of two polynomials equal to 0, this implies what? Either f of x is equal to 0 or g of x is equal to 0, right? In fact, if you're paying close attention to this, you can easily see that I can replace these z coefficients with what? Yeah, I can replace it with real numbers, complex numbers, rational numbers. Certainly a field will do it. I think if you think harder about it, even if we just took coefficients from an integral domain, I think we'd still get that this was an integral domain. But anyway, that's my example. This next example is a little bit snazzier. Here I'm going to look at functions from a set to a ring, where S is non-empty set and R is ring. So if F is an element of this thing, in other words, F is what? It's a function from S to R. It's an R-valued function of S, to be more precise. If I take G and F like this, all right, then I'll define F plus G of X to be F of X times G of X, and I'll define F times G of X to be F of X. I'm sorry, it's supposed to be a plus there, right? F of X times G of X. So basically just the pointwise addition and multiplication of functions, and you can easily sort through it that with this definition of addition and multiplication, it's commutative, it's associative with respect to addition because the ring has those properties, and likewise for the multiplication, you get the distributive properties are naturally inherited from the range of the function. You can check it. So this gives us a way of creating new rings from just looking at function rings. This is a ring which is made of functions. Let's see here. Another way you could create an example. Let's see here. Excuse me. I'm going to get rid of my integer example because it's done. Example 5. So example 5 is just basically R equal to a field, right? I mean, we've talked about fields before. I would just point out that, our favorite fields, in other words, the rational numbers, the real numbers, the complex numbers, and of course also Z mod of P. Well, I talked about that already, but these are all fields. And I would just point out that every field, of course, is a what? Is an integral domain, right? It's got no zero divisors. But it's stronger than that, right? Every field is an integral domain, but not every integral domain is a field, right? The condition of being a field is a stronger condition. And the condition of being a ring, well, that's a weaker condition than integral domain, right? We have lots of rings which are not integral domains. So there's some kind of like tower of ideas here to think about. But anyway, I should point that out, of course. Example 6. Actually, example 6 and example 7 are ways to build new rings from old. First of all, if R is a ring, then we can build R n by n, right? Which is just going to be Aij such that 1 less than or equal to I, comma j less than or equal to n, and Aij is an element of the ring. In short, n by n matrices with elements taken from the given ring, this forms a new ring called the matrix ring. How do you define addition? Like A plus B, you define it component-wise. So like A plus B, ij is equal to Aij plus Bij for all I and j. And the product of two matrices in the matrix ring is defined to be the sum k equals 1 to n, Aik Bkj. You're thinking, oh man, I thought I was free of that. No, it's back. So there you go. That's the definition of the product of two matrices in the matrix ring. You can prove that this product is associative. It is, of course, not commutative, right? There is an identity, right? So Rn by n has unity. Well, I don't know. Does it have unity? It has unity 1, 1, 1, provided R is unital. With 1 being the unity. Then the diagonal matrix with the unity down the diagonal is the unity for the square matrices over R. This is not an integral domain. Definitely not. Definitely not an integral domain. Notice, in addition, it's non-commutative, right? And also you can have something like this. 1, 1, 1, 1, minus 1, 1, minus 1, 1. What does that give you? Oh, I'm sorry. Minus 1, 1, minus 1, 1. So this gives us what? This gives us 0, 0, 0, 0. So not only is it not commutative, it's got 0 divisors out the wazoo, at least in the case that one's in your ring. By the way, if one's in the ring, minus one's also in the ring, because ring is closed under additive inverses, right? Let's see here, what else can we say? We've actually talked about the group of units of this thing before. U r n by n would be a and r n by n, such that the determinant of A is an element of the units of the ring. So this is assuming for R unital. If R is a unital ring, then you can talk about the group of units in the matrix ring. It's the matrices for which the determinant's a unit. And then finally, example 7. Example 7. If we have rings R1, R2, Rk rings, then we can form a new ring R by the Cartesian product of the rings, right? Where, as you might suspect, x1, x2, xk plus y1, y2, yk, and the product are defined component-wise. I'll just skip the second one here for the sake of brevity. I'm not telling you anything terribly surprising here, but we can form the external direct product, although I don't, I'll just say the external, I'll just say the product. We can form the product of rings by defining the ring operation component-wise. So we just inherit the addition and multiplication of each of the, so for example, the ith slot is based on the addition and multiplication from R sub I. So I'm almost done with the notes for this section. Let me show you what I got done so far. Where did I put it? Sorry, I was originally supposed to have 2 lectures for this lecture, but then something happened. What was it? I got sick, right? Yeah. So it's cramping my style a little bit. And if you're a little bit lost right now, you should become unlost as soon as you read chapters 12 and 13 of Galilean. This stuff is really not that hard. I mean, my example, fleshing out the details of the matrix units, there may be something a little bit mysterious there, fine, agreed. But mostly what we're trying to get used to at the moment is just the basic terms and conditions, right? So we haven't really covered a difficult theorem today, I don't think. Certainly nothing as complicated as, I don't know, did we really go over that complicated a theorem that I actually required you to know? I mean, I didn't require you to know the CELO theorems. So throwing those out, and Birdside's lemma, that's out. So there's just a lot of things, right? It's more question of volume than difficulty, I think. Anyway, that is my opinion. That may not be yours, and that's fine. You're, of course, entitled to your own opinions. We're not living in Hillary's America yet. Let's see here. Okay, so these are things we get automatically once we are considering a ring, right? Once you ring the basic axioms, the commutative group under addition, and the distributive properties, the associativity of multiplication, from those and the existence of 0, we automatically get these other bells and whistles. Like a times 0 is 0. This is not an axiom. This is a derived consequence of the ring. And here's the proof. Like 0 plus a times 0, well, that's equal to a times 0 because 0 is the additive identity. But then by distributive property, well, on the other hand, 0 is 0 plus 0 because it's the additive identity. So I'm just replacing 0 with 0 plus 0. But then by distributivity, that is a times 0 plus a times 0. And then you got this equal to that. By cancellation property of groups, it follows then that a times 0 is equal to, sorry, I can't do this right. A times 0 is equal to 0. It's the other way around technically, but you know. And then the right multiplication being 0 is very similar. Down here is the proof that I prove 2, which is a times minus b is equal to minus a times b is equal to minus ab. These are derived consequences. These make very easy test questions if you've studied them. But I don't know. I mean, personally, I can spend a lot of time trying to prove one of these if I go the wrong way. So my advice would be is you try to work these out for yourself. Don't spend too long on any given one. If you don't get it right away, you should do something else and come back to it, Anyway, so these are things we know. Basically, rings allow us to multiply and add and subtract like usual, right? Saying something's a ring, but so the fantastic thing here is every theorem we prove about a ring pretty much automatically applies to almost every example that you know and love, right? If you start thinking about it, polynomials with integer or real or complex coefficients, matrices made of things from a ring. So you notice that matrix could be a matrix of polynomials. Oh heck, it could be a matrix of matrices. It could be a matrix of matrix of matrices. It could be a matrix of, okay, I'll stop. It's endless, these stupid examples. By the way, this product ring is, by the way, not an integral domain. Even in n equals 2 cases, it's easy to see why that is, but I'll shut up. Okay, so subring, what's a subring? Well, a subring is a subset of a ring, which is a ring with respect to the addition and multiplication of the ring. Guess what? We got a subring test. Non-empty subset of a ring is a subring if it's closed under subtraction and multiplication. That is, for each a and b in the ring, we have a minus b, and ab is again in the ring. Aw, come on. Really? This is an S? This is important. This isn't, don't worry, I haven't posted these yet. I'll try to fix it before I post them. But this is most certainly an S. And this is most certainly an S because otherwise it's not a test on S. Right? I mean, duh. So the proof of the subring test is totally uninteresting. You can read it. It's the same as the proof of the subspace test from linear. It basically just says, hey, if it's in the subspace, it's in the vector space, and so all of the axioms hold for those elements. And the condition closed under subtraction and closed under multiplication makes the axioms hold for the elements, right? Anyway, here's a good example. The even integers form a subring of the integers because if you take 2x, 2y, and the even integers, the difference is again an even integer. The product is again an even integer. You need to show something like this to prove that claim here, right? Like you shouldn't, I mean, I don't know. I guess if it's, let me shut up. Anyway, so it's non-empty, right? 2 is in there. Or you could put 0 in there, or you could put a million. I mean, whatever. Just one even integer will do to show it's not empty. And so it's a subring. It's not unital, right? Because 1, which is what you need to be a unit in there, is not in there. So the subring is not unital, despite the fact that the integers are unital, right? We lose the unity in this case. It's also nice to notice the odd integers are not a subring. This example is going to weird you out. So Z6, basically look at the even Z6 integers, right? 2Z6. That's a subring for essentially the same argument up here, right? The difference in product of even things is again even, also in the context of Z6. You can sort through the proof. Here's actually multiplication table and addition table. So you got 2 tables for a ring, right? Here's the addition, boring. Multiplication, kind of interesting. Of course, 0 multiplies to 0, so that's kind of like a snooze. But this is weird. Look at this. So 2 times 2 is 4. And 4 times 4 is 4. And look at that. What is that? That's the multiplication table for Z2. I mean, well, not Z2, but it's the multiplication table for like minus 1, 1. Right? You can, anyway, you can explicitly check that 4 times s is equal to s times 4. The look on his face was very funny. I don't know. Anyway, so 4 times s equal to s times 4. So in other words, 4 is 1 in this subring. So this subring has a unity, and weirder still, the unity in the subring is not the unity in the superring. 1 in Z6 is 1. The quote-unquote 1 in this subring is 4. Multiplication is weird in rings, all right? So you shouldn't trust your intuition too much when you think about multiplication. Addition, you probably won't be wrong, because addition is just a group structure, and we're familiar with that. But the multiplication is weird. Anyway, here's some other exciting examples, which I'll talk more about next time. Anyway, thanks, guys. Oh, I should give you back your test, but you can turn that off, because I'm about to say